Hello and welcome to Chemistry Workshop. This is a start of a series where I'll showcase some amazing research in chemistry, mainly focusing on total synthesis. Today we'll look at the total synthesis of Oridonin by the Law Group at Peking University. The traditional Chinese herbal medicine, rubicins, has been used to treat the common cold, pharyngitis, and aphthous ulcers, and it has been included in the Chinese pharmacopoeia since 1977. One of its active compounds is a white solid and a natural terpenoid, Oridonin. It is of great interest to synthesize and investigate Oridonin due to its anti-inflammatory, anti-cancer, hepatoneoprotective, and lung protective activity. The molecule has a strained and sterically hindered carbon skeleton, possessing a polycyclic core built from only 17 carbon atoms. Apart from its skeletal complexity, it has two hard-to-synthesize quaternary stereocenters on the same ring. It is also heavily oxidized and thus requires an abundance of late functional group manipulations. We start from the retrosynthetic analysis of Oridonin. The Law Group noticed that the singlet oxygen reaction on 2 can afford Oridonin through an allylic hydroperoxide. From 3, a 1-2 shift from opening an epoxide ring and deprotection of the hydroxyl groups through reduction will result in 2, with the correct configuration of the hydroxyl group on the British carbon. Through an acetylene rearrangement, or another 1-2 shift, the alpha hydroxyl carbonyl at carbons 6 and 7 with concurrent ring expansion could be achieved, and with an epoxide formation, 3 could be produced successfully from 4. The ring contraction provided a 5-membered ring, which revealed a key idea behind the Oridonin synthesis, the interrupted Nazarov reaction. The recognition that a cyclopentanone ring could be fashioned in a single step through the Nazarov reaction while trapping the cationic intermediate to construct a 7-membered ring simultaneously demonstrates great insight. The Law Group anticipated that while the Nazarov cyclization would construct 2 stereocenters, the tethered allyl trimethylsilane, a nucleophile, could attack the cationic intermediate from its underside and form the 7-membered ring, and another pair of stereocenters alpha to the carbonyl. Thus, it is conceivable that through an interrupted Nazarov cyclization, 4 stereocenters, including 2 quaternary ones and 2 rings, could be formed while being suitable for late-stage functionalization to afford Oridonin. Besides participating in a breathtaking interrupted Nazarov cyclization, the allylsilane moiety serves another function. After its attack on the cationic intermediate, the trimethylsilyl group leaves behind an exocyclic double bond. This then serves as a site for an ene reaction with singlet oxygen, and then after a deformylation reaction, the endocyclic double bond, which serves as a future basis for the oxygen ring and a carbon-14 hydroxyl group, will be put in place. Then a carbonyl addition will afford 4 from the Nazarov cyclization product 5. Then, converting A to an organolithium reagent and undergoing a carbonyl addition with 9, followed by oxidation with yield 7, the precursor required to perform this Nazarov cyclization. Finally, the 2 building blocks 8 and 9 could be constructed from simple starting materials, and they could be a logical starting point for this total synthesis. The synthesis of Oridonin starts with 3-methyl-2-cyclohexene 1-one starting material 1 and 2,2-methylcyclohexane 1-one starting material 2. 3-methyl-2-cyclohexene 1-one and the organoaluminum reagent prepared from terbutyl dimethylsiloacetylene and dival H underwent an enantioselective 1,4 addition, resulting in 10. Then, 10 is treated with iodine chloride to 411, which undergoes a palladium-catalyzed cross-coupling reaction with an organozinc reagent and furnishes the allyl trimethylsilane group. Then, 12 deprotonated by NaHMDS selectively on the less hindered alpha carbon forms a vinyl triphate, which forms the carboxylic acid 13 through a palladium-catalyzed carbonylation. Then transforming this carboxylic acid into its corresponding WinRib amide and then performing a reduction by dival H furnishes 9 in an 11.8% yield from 3-methyl-2-cyclohexene 1-one over 7 steps. The synthesis of building block 8 commences with 2,2-dimethylcyclohexane 1-one starting material 2. Through a bromine formulation with the bromine analog of Vosmeyer-Hack reagent and a pennic oxidation and an esterification by methyl iodide, the ester 15 is formed smoothly with a yield of 40.2% from starting material 2. Then it is subjected to allylic oxidation by chromium trioxide to form 16, which undergoes an asymmetric reduction by borane and using X-oxazoborolidine as an asymmetric catalyst and results in 17. Some might notice that a wrong catalyst is used here, producing an inverted stereocenter at C1. However, this inverted stereocenter serves another function, and that would reveal itself later. Finally, 17 is exposed to sodium hydride and benzoyl bromide to protect the hydroxylic groups, and 8B is obtained. Then, performing a lithium halogen exchange on 8B with tertiary butyl lithium and adding to the carbonyl of 9, we get an alcohol which PDC then oxidizes to obtain 7B. Having witnessed the synthesis of fragments 8B and 9, and then the intermediate 7B, we're now in a suitable position to address the 5-metal ring N5 and the selective interrupted Nazarov reaction. With the divinyl ketone center established in 7B, a Nazarov cyclization could be carried out to form the 5-metal ring N5B. And as we know, this is a Nazarov cyclization carried out by heat, and thus it follows the mechanism with a conrotatory ring closure. Here it is a previously established incorrect stereocenter at C1 and the benzyl groups at carbon 1 and carbon 20 that produces the fantastic torcoselectivity. The steric strain induced by requiring a benzyl group at C20 to flip through the cyclohexene ring, disfavors the counterclockwise rotation and promotes a clockwise rotation that produces the correct configuration around the ring. Also, the inverted C1 group opens up space for the benzyl group at C20 to rotate clockwise, further promoting the clockwise rotation and producing the cationic intermediate. Then, with the cationic intermediate produced, it is quite interesting to know that there are only 3 atoms between the nucleophilic allyl-trimethylsilane moiety and an electrophilic cationic part produced by Nazarov cyclization. A close spatial relationship between the 2 reacting groups and formation of 5 or 6-membered rings with small ring strain would typically produce a facile cyclization. In this case, the tethered allyl-methylsilane group approached the cationic moiety on the backside and smoothly produced a 5-membered ring while closing the 7-membered ring in the final product with the correct configuration. It is truly astonishing that this insightful interrupted Nazarov cyclization can produce 4 correct contiguous stereocenters in one step. After constructing this tetracyclopentadecane core, we can see expanding the cyclopentanone ring to a cyclohexanone ring and heavy oxidation of the carbon skeleton is still required for completing the Oridonin synthesis. Firstly, intermediate 5B is subjected to an ene reaction with singlet oxygen excited by TPP and an acetic anhydride, forming 18, which is then treated with a rhodium catalyst to achieve deformylation, resulting in intermediate 19. Then, this cyclopentanone is attacked by vinyl lithium, and an endocyclic double bond generated in the ene reaction is epoxidized by NCPBA. The group had tried to oxidatively cleave the vinyl group attached through this carbonyl attack, but all attempts had failed, possibly due to steric factors and the high oxidation level of the skeleton itself. Still, the group realized a ring expansion with a pinnacle-like reaction by attacking the vinyl group with electrophilic bromine, and then a 1-2 shift to result in a ring expansion. Then, oxidizing the benzoyl protection groups to benzoyl ones with octavalent ruthenium and eliminating the bromine with DBU as base resulted in enone 22. And subjecting it to upjohn dihydroxylation results in the diol 23. Now we're not far from the goal of this total synthesis, Oridonin. By subjecting 23 to a Lewis acid, in this case, the lower group found ethyl aluminum dichloride to be the most effective. A 1-2 shift is achieved with carbocation generated by the opening of the oxyring ring, which completed the carbon skeletal structure of Oridonin in the intermediate 24. Then, reducing the carbonyl using lithium and aluminum hydride and cleaving the exocyclic 1,2 diol with sodium periodate with concomitant intramolecular hemiketal formation, we arrive at an intermediate 25 with a fully constructed ring structure of Oridonin. Now, it is time to address the configuration of the chiral centers. We can recall that the configuration at C1 is the opposite of that in the natural product as a method to enhance the torcoselectivity of the Nazarov cyclization, while the configuration at C6 is also inverted due to the hydride attack by lithium and aluminum hydride from the less hindered phase of the molecule while chelating to the hydroxyl group as C7. The lower group anticipated that oxidation of those hydroxyl groups to carbonyls and a reduction could furnish the correct configurations. Thus, protection with acetonide or other of the other hydroxyl groups is first applied, and oxidation of the hydroxyl groups at C1 and 16 affords the diketone 26. Then, selective reduction of C1 with dibial-AH and reduction at C6 with sodium bis 2-methoxy ethoxy aluminum hydride afforded 2 diastereomeric products 2A and 2B, only differing with the configuration of the hydroxyl group at C6. The product with the incorrect configuration 2B can then be recycled with the same oxidation reduction strategy. And then, finally, the product 2A is subjected to another ene reaction with singlet oxygen to produce an allylic hydroperoxide, and the synthesis concludes with the formation of the alpha-beta unsaturated ketone from said allylic hydroperoxide with BOC2O, and we arrive at the final product, Oridonin. The synthesis of Oridonin by the Law group is an outstanding achievement in total synthesis. The use of a selective interrupted Nazarov cyclization and a 1-2 shift to construct a main carbon skeleton is fascinating and displays great ingenuity and insight, and this work provides a novel strategy for the novel synthesis of incaranoids. I hope that this video on Oridonin is interesting. If you have any questions or suggestions on how this can be done better, feel free to put them in the comment section. The next episode will be about the synthesis of cyclobutadiene B by the Yang group in 2021. I hope you all have a great day and see you next time. Thank you.